SwayamPrabha. Digital India. Educated India.
Welcome everyone to another session of supplementary videos, and today we will be discussing the basics of coordinate systems in a generic fashion. Okay, so that's the today's topic. So let's start. The topic of today is coordinate systems. Okay, so up to now, I think so from our undergraduate studies as well as our high school studies, we have seen the use of coordinate systems quite a bit, and we have different kinds of coordinate systems. Kinds of coordinate system. And the two generic way of characterizing is based on, let's say, so we call one class of coordinate systems a rectilinear coordinate systems, and the another one of is the generalization basically is the curvilinear coordinate systems. Okay, so example of rectilinear coordinate system is Cartesian coordinates. For example, we know the Cartesian coordinate systems. Cartesian coordinate system. So that's a rectilinear. And here the word rectilinear means that the constant, let's say we have, let's draw the Cartesian coordinate system. We have the x, this is the y direction, and then this is the z direction. So x equals to constant, y equals to constant, or z is equals to constant. These all defines planes. Okay, or in two dimension you can think about them as lines, the defined lines, and they are linear, and so these are linear objects. Linear, so that's hence the thing rectilinear. Okay, and on the other hand, examples of curvilinear coordinates are, for example, polar coordinates, and this is in two dimension, and we have the cylindrical coordinates, and then we have spherical coordinate system, and that is in 3 dimension. Okay, so these are example of curvilinear coordinates, because as you can see, let's take an example for draw the polar coordinates. So if you see, the polar coordinates is defined by some origin, and then so here the iso can think about, let's say in a 2-dimensional rectilinear coordinate, we draw the 2-dimensional rectilinear, that is a Cartesian coordinate, let's say x and y. So here the constant x is equal to constant line and y is equal, so this is y is equal to constant line, y is equal to constant. Similarly, in x is equal to constant line is again a straight line, x is equal to constant. Okay, so as you can see, these are straight lines, linear, and also they are orthogonal. So these all are orthogonal coordinates which we are discussing, whether it is Cartesian. In a fashion, a coordinate system can be arbitrary, so we can have coordinate systems which are, let's say, like this. So where the angle between axis is not 90. Those are oblique coordinates. So these are oblique coordinates. So those are also useful in certain types of problem, but for this material, this segment specifically, what we'll be dealing with is orthogonal coordinates. Okay, and similarly, for example, here in terms of the curvilinear space, we have the polar coordinates. So if you have a pole, and from which you have different radial directions. Okay, so basically, and these directions are categorized by an angle theta, and then you have concentric circles. Okay, so that represents polar coordinates. So here any point is represented. So for example, in a Cartesian coordinate, any point is represented by a set of three numbers, 3 tuple, x, y, z. In polar coordinates, this is a 2D representation. So any is represented by an r and theta, where theta is the angle from some reference axis and r is the distance of the point from origin, which is also known as the pole. Okay, so that's so this is an example. As you can see, this is a curvilinear coordinate, because one of the iso lines, as you can see, are spherical. Like here, these are circular isolines, which are the radial lines, which represents r equals to constant. Okay, on the other hand, the other isolines, theta is equal to constant, those are still linear objects. Okay, but here, since one of the coordinate is, as you can see, it's non-linear, hence the polar coordinate belongs to the curvilinear coordinate systems. Okay, and the extension of the polar coordinate in a higher dimension is the cylindrical coordinate, and we also have the spherical coordinates. Okay, so these are some of the basic examples of coordinate system that we use in all of physics. Okay, so let's say we have a Cartesian orthogonal coordinates. Okay, so this in the origin, we have the x-axis, y-axis, and the z-axis, and and this is a Cartesian coordinate, as you can see, because it's linear. It's a rectilinear coordinate system, and it's orthogonal because these all angles, as you can see, are 90 degrees. These are 90 degrees. So any point in this coordinate space P, let's call that point P, that is represented by three numbers, a set of three numbers, x, y, z. Okay, so that is like okay, so these coordinates are x comma 0 comma 0. This is 0 comma y comma 0. If you see here, this is x comma y comma 0. And similarly, if you draw like this is 90 degree. This point is 0 comma 0 comma z. Okay, so you see this length is x, this length is y, and this vertical height length, that is z. So that's a general representation of a point in cylindrical sorry for that, this is for in Cartesian coordinates. Okay, the same point can be represented in a cylindrical coordinate system in a different way. So let's say, so this is, I will say, Cartesian coordinate. Okay, so let's do cylindrical coordinate system. So let's again draw the Cartesian coordinate just for reference purpose, because that is the system in which it's always easier to write things down. X, Y, Z. that is the general our Cartesian coordinates. And let's say we have our point P whose Cartesian components we know they're given by x, y, and z. Okay, and we know what those are now. So okay, as we did it before. So same point P, since it is in three-dimensional space, needs three tuple to represent the point, but we can use a different point. So this same point xyz is equivalent to, in cylindrical coordinate systems, to which is known as, let's call that rho theta and z, where rho is the distance from origin to this point. Let's call that point A. So this distance from the origin to point A, that is rho. The angle that OA makes with the x-axis, that's the theta, that's the azimuth angle, and this is the height, which is z itself. Okay, so that's a cylindrical coordinate system, and you can see from this triangle like OAB, we can write a representation of, or the relationship between the Cartesian and the cylindrical coordinates. And the representation is, if you see properly, the x coordinate is rho cosine of theta, the y coordinate is rho sine of theta, and the z coordinates stay as it is. Okay, because that in that direction it's the same as the Cartesian. Okay, that is the transformation, as you can see, from Cartesian to polar coordinates. Okay, and so that means given rho theta and z, we know what is xyz. We can write the reverse transformation. So the inverse, let's write the inverse transformation. So this is from this is given polar or cylindrical to Cartesian. Okay, so rho theta z are given, and using these set of equations we can find what is x, y, z. Okay, let's write the inverse transformation. The inverse transformation means we are now given x, y, z, and then we have to write rho theta z. We have to find out. This is unknown. Okay, so if you see that is quite easy to write just from these two equations. Rho is square root of, it's a distance, this is basically rho, that's x in the xy plane, x square plus y square. Okay, that's rho. What is theta? Theta is, if you see, is tangent. Okay, if you divide this equation by this, the second one, this one by this one, we'll get the tan theta, which is y over x, and z stays as it is. Okay, so these are the inverse transformations. Okay, then these are the inverse transformations. Okay, so we understood about cylindrical coordinate systems, and this is Cartesian coordinate systems. So let's go to spherical coordinate system. Spherical coordinate system. So let's again draw the Cartesian coordinates for reference. This is our x Cartesian, y z, and this is the point P whose x was given by xyz in Cartesian. That point was given by rho theta or rho, I think so, we called it, yeah, so we called it here theta z. So this was in Cartesian, this was in cylindrical, and now we represent the same point in spherical, and that spherical coordinate system is given by a set of numbers which is r, theta, or let's write it r, phi and theta, r, phi and theta. Okay, and note, by the way, in the cylindrical coordinate system we use this theta, and here also we have theta. These two are different, we will see. Okay, in cylindrical coordinate system theta is the azimuth angle, and in spherical polar coordinates phi is the azimuth angle, okay. So this point, the distance of that point from the origin, that is r, okay. And similarly, let's drop the projection of that point onto xy plane, and this angle is the azimuth angle known as phi, and the angle between OP and the z axis is theta, and that is known as the zenith angle. Okay, so these are the three r, phi and theta are the three set of numbers that represents the same point P in spherical coordinate systems. So let's write a similar relationship between the Cartesian and the spherical as we did it for cylindrical. So you see, just draw the projections. I will see the x equals, this is x, and if you see, that is r sine theta, which is this length. This length is r sine theta, and the projection of that on the x-axis is r sine theta cos phi. Okay, so that's x. Similarly, y will be r sine theta in phi, and if you see, the z will be the r cosine theta. Okay, clear on that? So similarly, let's write the inverse transformations as we did for, so if you see the inverse transformations, r is square root of the distance from the origin, x square plus y square plus z square, and phi can be represented by dividing, let's say, this equation by this equation, which is, you will see, tan inverse y over x, and theta is cos inverse, that is, you can see from here, it's r z over r, so that's z over r is square root of x square plus y square plus z square. Those are the inverse transformation in spherical coordinate system. Okay, so one very important point that we need to keep in mind is the range of the variable. So in the Cartesian coordinates x, range is minus infinity to plus infinity. Similarly for y, and same thing for z. So it's unbounded in all the three directions. Okay, it's infinite. For the cylindrical and the spherical coordinate systems, let's write that down. So for cylindrical coordinate system, we have, it's given by rho, theta and z. If you see, cylindrical coordinate is given by rho, theta and z, and rho goes from 0 to infinity, theta is the azimuth, okay, this is the azimuth, and that goes from 0 to 2 pi. So you see in that direction it is bounded, and z is in unbounded again, so it's from minus infinity to plus infinity. Okay, let's write the spherical coordinate system. And that is given by r phi, where phi is the azimuth now and theta is the zenith. So r, see, 0 to infinity, phi is 0 to 2 pi, and theta is 0 to pi. Okay, so it's bounded in two directions now, because this represents the surface of a constant r will represent a surface of a sphere in the spherical coordinate system. Okay, so that's the generic understanding of all the three types of coordinate systems, and we will generalize all these ideas so that what we want to do is basically vector calculus in all these coordinate systems. That's the general our main goal. That means we need to know how to write quantities like a vector, the gradient of a vector, divergence, the Laplacian. So that's the aim that we have in our mind. So we have to represent all these quantities in different coordinate systems. Okay, so that's the goal, as you can think about. Okay, so before moving on to the writing, or let's say discussing the vector calculus in various coordinate systems, an important point to note down is knowing the volume elements. So for example, the volume element, and that means let's draw an infinitesimal volume near to point at point P, basically centered at point P, and you see that it is a cuboid, something like this. Okay, and that volume of that small elementary volume in cylindrical let's call it in Cartesian coordinates. Let's do it for Cartesian coordinates. So let me write down the volume elements in various coordinate systems, various coordinate systems. So we have this x, y, z, and this was the point, let's say P, given by x, y, and z. Okay, so a small elementary volume at that point P will look something like this. It's a cuboid. Okay, and that elementary volume dV has magnitude dx, dy, dz. Okay, and let's do it in cylindrical. So just by the nature of the cylindrical coordinate system, you will see that, let's say we have again the coordinate system and this point P now, but that point, let's see, So this is rho, that is theta. Okay, so this is the point P, so a small volume element there will look something like this. As you can see, so if you see the sizes of this small differential volume can be, so this, the size parallel to the z-axis is dz, this, which is parallel to, let's say, the xy plane, this is basically this length, as you can see from this. So this is rho and this is theta. This elementary part will be, this is rho d theta. Okay, and this is measuring in the rho direction, so this is d rho. Okay. So the dv, the elementary volume, becomes rho d theta dz d rho. Okay, and let's do the same for spherical. In spherical coordinate system, spherical coordinate system, okay, so let's write the volume element for spherical coordinate system. So this is the x, y, z, and any arbitrary point P, and in spherical polar coordinates this is given, this is r, projection of that on the xy plane, this is the azimuth phi. So this, in the system we have r, phi, and theta, the zeniths, and this is theta. Okay, and so if you draw the coordinate system, or let's say the elementary volume in this coordinate system, this will look like and this gets, so here we have the two sides of it, and the third direction is in the radial direction, so this has to be projected in the radial direction. Okay, so that's d. This, let me redraw it. This is the point P, this is the direction of dr. Okay, this is one direction, and then we have another direction which is parallel to this, do something of this. Okay, so this will represent element which looks something of like this, and something like this. Okay, so bear with me, my drawing for here, it's difficult to draw digitally. So let's write dv. This is the volume element, and if you see the 3 dimensions of the cube are, so it will be r sine theta d phi. So that's this in this direction, that's r sine theta d phi, that's parallel to that direction, times r d theta, which is this direction, times dr. Okay, so that's the volume element in the spherical coordinate system. Okay, that's the generic volume element. So it's, let me write it in a better way. So the dv is dr r d theta and r sine theta d phi. So these are the 3 directionalities, if as you wish. The radial, this is the zenith, and this is the azimuthal direction. Okay, that's the volume element in spherical coordinate system. Okay. So now we will go in to figure out the exact how to write the various vector components, like the gradient, divergence, Laplacian of any general arbitrary vector field in these various coordinate systems. Okay, and that we will do in the next segment. So that's for this segment. Thank you for watching. Okay, and see you in the next segment.